This video is to demonstrate the workflow between Feko and HyperStudy for antenna design optimization using machine learning. This workflow between Feko and HyperStudy is demonstrated through the example of a patch antenna designed for GPS applications. The antenna is a slotted square patch on a metal-backed FR4 substrate. This design can be optimized by adjusting the size of the patch, slots, and the feed position. Here, we basically have 5 design parameters in terms of patch size, slot length, slot width, feed position, and the distance of the slot from the edge of the patch. The goal here is to optimize the antenna design to have the best impedance matching at the given GPS operating frequency of 1575 MHz. The characteristic impedance of the feed is 50 ohms, and here is the initial response of the base design for a 50 ohm reference impedance. As you can see, we have a decent impedance matching with a reflection coefficient of -8 dB at the GPS operating frequency. But we would like to improve it further using HyperStudy. Coming to HyperStudy, Altair HyperStudy is a multidisciplinary design exploration, study, and optimization software for engineers and designers. Using design of experiments, meta-modeling, and optimization methods, HyperStudy creates intelligent design variants, manages runs, and collects data. Users are guided to understand data trends, perform trade-off studies, and optimize design performance and reliability. HyperStudy's intuitive user interface, combined with its seamless integration to Altair HyperWorks, makes design exploration technology accessible to non-experts with state-of-the-art design exploration, meta-modeling, and optimization methods, data mining tools that are easy to understand and interpret. Most importantly, direct interface to most popular CAE solvers, including Feko. The basic workflow between Feko and HyperStudy starts with creating a parametric design in Feko. Once the initial design is created, we run the model and plot the desired output data, which is used to define the optimization goal in HyperStudy. HyperStudy is then launched by running the macro in post-Feko, which automatically creates a new study by loading the Feko model and all the design variables. The initial setup is then finished in HyperStudy and an output response is defined. Basically, HyperStudy reads the data plotted in post-Feko and makes it available to define the output response on which the optimization goal can be set. Once HyperStudy understands which model to use, the available design variables, and the output from the initial setup, we can then perform design exploration, then create surrogate models from the design exploration data using the machine learning algorithms within HyperStudy, and also perform optimization using the surrogate model. The main advantage of using the surrogate model for optimization is the time saving. Depending on the size of the model, a solver simulation may take anywhere from minutes to hours for each iteration, whereas the surrogate model takes only a fraction of a second. Here is a comparison between the initial design and the optimum design of the patch antenna. You can clearly see the improved impedance matching at the GPS operating frequency with a reflection coefficient of almost minus 30 dB. Now let's go through the actual demo of the entire process described so far. This is the CAD-FECO interface where you can see the initial design of the slotted square patch on a metal-backed FR4 substrate. In the model tree on the left, we can see all the design variables used to create the parametric design. Scrolling down, we can see all the geometry parts. If I open one of the parts, you can see that rather than using hard numbers, we have the variables used to define the position as well as the dimensions of the given part. And this design is ran over a frequency range from 1.45 gigahertz to 1.7 gigahertz. So this is already simulated. I can open post-FECO to look into the results of the initial design. Post-FECO is being launched. And this is the interface of post-FECO, where we can see the geometry of the square patch. Here I am adding a Cartesian plot and then plotting the source data, which gives us the reflection coefficient. This is in linear scale, converting it into dB. Now we can see the initial response of the base design of the slotted square patch. Once we have the output data plotted in post-FECO, we basically need to save this post-FECO session. And once it is saved, from the application macro drop-down menu, we go to the utility section where we can see the HyperStudy macro. We click on that optimize model in HyperStudy. Once we click on that, it will run that macro script. Once the macro is finished running, it will launch a pop-up window that basically has a study label. So we can obviously change the study label. So I'm going to change this to GPS patch demo, and also a folder where all the study models will be saved. I'm going to save this into a demo folder, so GPS patch _demo. Basically, under additional options, we can see it is going to create a preference file as well as launch HyperStudy. When HyperStudy is launched, the FECO model is loaded as well as all the design variables are read into that HyperStudy session, and the output response, whatever we plotted in post-FECO, that will also be available in HyperStudy to define the optimization goal. I'm going to click OK. So here you can see it is going through different steps where it is running HyperStudy in the background, reading the FECO model, setting up the environment. So now it finished creating the HyperStudy session. If I click OK, then it launched HyperStudy. So you can see here, this is the name of the study, GPS_patch_demo. And we have under define models, the initial design is already loaded here. Now for design exploration, when we run this model, we can specify how many cores we want to use for each solver simulation under solver input arguments. I have 4 cores on my machine, so I'm going to specify to use all the 4 cores. That's minus NP4. So whatever new input I am giving in this HyperStudy session, it's going to change the initial definitions. So that is what I want. So I'm going to click yes. Moving on to the next step. So we can see all the design variables loaded into HyperStudy. I'm going to select only the design variables that I want to use for the optimization process, which is basically the feed position, the patch size, slot length, slot width, as well as the distance of the slots from the edge of the patch. And based on the initial values of these variables, HyperStudy also gives a default range, and we are fine with the default range. I'm not going to change the range here. I'm going to click on next. So in this one, what we basically want to do is we want to run this initial definition where HyperStudy will try to communicate with Feko, execute the Feko solver, extract the data, and make the data available in post Feko in HyperStudy. Okay. So let me do that. Run definition. So it is now writing whatever is required to execute Feko solver in the background, and then it will execute the solver in the background and then extract the data and make it available in HyperStudy. It is now finished. We go to the next stage. This is where we will define the output response that can be used to set the optimization goal. Once I click on add response, if I go to this expression, and under the expression builder, when we go to the data sources, that is where we can see the post Feko graph. Okay. So we have both the horizontal axis as well as the vertical axis values. Okay. So the quantity is the vertical axis value, which is the reflection coefficient, and the axis value is basically the frequency range. Okay. I'm going to select the actual quantity, which is the reflection coefficient, and if I click on insert, it is available under expression. I basically want to look at what is the minimum reflection coefficient. So minimum of the variable m1 underscore ds1, and we can see this is the value. I click OK. Now that expression is available. If I click on evaluate, now the value is also available. What this means is HyperStudy is able to read the Feko output response data and make it available as a quantity to set a goal in HyperStudy. Now under goals, we have the option to either minimize it, maximize it, or make it equal to certain value. Okay, so all these options are available. What we want to do is we basically want to minimize the reflection coefficient. Yeah. So that is what I set here. Click OK. So this is the initial setup. Next step after the initial setup is to perform a design exploration through a DOE study. We can add a DOE study by right clicking in the white space on the left, select add, and we can see the DOE option. For the definition, we will take it from the initial setup. Click OK. Expanding the definition, you can see the model is already loaded. All the variables are available and the output response is already defined. Now going into the specifications, here we can see all the different DOE methods available. I usually go with MELS. If you want to learn about all these different methods, you can give a reading in the HyperStudy documentation. For the number of runs, the default is 24. This is based on the number of design variables we have. But I usually go with a number which is number of design variables multiplied with 10. So we have 5 design variables. So I'm going to change this to 50. Click apply and go to next. Now you can see all the 50 iterations are added. Once we click on evaluate tasks, HyperStudy will run the Feko solver in the background by choosing different values for the design variables at each iteration of the DOE study. And the choice of the values depends on the DOE method we selected. At the end of the DOE study, we will be able to see which design variable impacts the output response more and which one less. So let's start running this one. I will click on evaluate tasks. And now you can see the execution started. The DOE is now finished. Going to the post processing. This is where we can see the Pareto chart. Here on the horizontal axis we have the design variables, and on the vertical axis we have the output response. Here we can see the slot length has the highest impact on the output response, whereas the slot width has the least impact. So if we vary the slot length, the output response, which is the reflection coefficient, it's going to change a lot. The next step after the DOE is to generate a surrogate model. To do that, once again, we can right click the white space on the left, select add. We already have the data from the DOE, so we are going to go with fit existing data, and we can use the definition from the initial setup again. Click OK. Once again, we can see the model is loaded. We have all the design variables. Now going into the specifications, these are the algorithms that we have. These are all the different machine learning algorithms. I would recommend to go with the default, which is fit automatically selected by training. So depending on the data we have, HyperStudy will automatically choose the appropriate machine learning algorithm to generate the surrogate model. And for the input, we are going to use the data from the DOE. We click on apply. If you go to the next stage, click on evaluate tasks. The data is evaluated. Now going to the post processing, this is where we can test or check for the accuracy of the surrogate model. Under diagnostics, there is this R-square value. So if this R-square is greater than 0.8, it indicates that the model has good predictive quality. If it is greater than 0.9, that's even better. So here we have greater than 0.8, which is good. We go to the scatter and plot the response from the surrogate model to the response from the actual DOE data. So you can see they're all aligned along this diagonal axis. That means our surrogate model is able to predict the output response accurately. Now that we have the surrogate model, the next step is to use that surrogate model and perform optimization. We can add optimization setup once again by right clicking the white space on the left, select add. This time we are going to select optimization, and the definition we will choose it from the surrogate model. Click OK. Expanding the definition, you can see the models are already loaded. Now here under the output response, what we want to use is we want to use the output response from the surrogate model. This way, instead of running the actual physical model in the background for every optimization iteration, HyperStudy is going to use the surrogate model. I'll change it to the fit, evaluate, going to the next one. So this is where we can see all the different optimization algorithms. ARSM is a local optimizer, whereas GRSM is a global optimizer. So I'm going to go with the global one. And for the number of iterations, since we are using the surrogate model, each iteration will take only a fraction of a second. So we can run hundreds or thousands of iterations in a matter of few seconds. So we will run this for 500 iterations. Apply. Next. You can click on evaluate tasks. Now you can see here, it is taking only a fraction of a second for each optimization iteration. It's going through pretty fast. So this is the advantage of using the surrogate model for optimization. You can run hundreds or even thousands of iterations in a matter of few seconds, no matter how big is the original physical model. Our GPS antenna model, for each iteration, if you are running the Feko solver in the background, it will take maybe close to a minute to run. So if you are running 500 iterations, it might take close to 500 minutes to run that. Whereas using the surrogate model, in a matter of few seconds, we will be able to run 500 iterations of optimization. It's already finished. All the 500 iterations are completed. Now if I go to post processing, we can look at the summary. So this basically gives us the different values that are chosen for each design variable at each optimization iteration, and the optimal value as well. Under evaluate, if you go to the evaluation data, we have these green ones, which are basically nothing but the optimal runs. Out of all these 500 iterations, so we have the 57th iteration as the optimal one. So what we need to do next is take the values of all these 5 different design variables and plug this into the initial model to update that model with these optimum values and run it. We already did that, and when we used the optimal values in place of the initial values and rerun the antenna design, now we can see how the reflection coefficient changed. So the blue curve is the initial design, whereas the red curve is the optimal one. The reflection coefficient at 1575 megahertz is close to minus 30 dB, whereas initially it was like around minus 8 dB. So that is the advantage of using optimization. We'll be able to optimize a given design for our required specifications. So through this demo, we saw like how we can use HyperStudy to generate a surrogate model and use it to perform optimization.